although this conversation is really supposed to be about differential equations, what we're going to use as our instrument is going to be the concept of a drag force that is somehow proportional to the velocity. There are two different types that we've talked about. There's drag forces that are directly proportional to the velocity, and there are drag forces that are proportional to some function of the velocity. These are the most common that are used as a means of example in physics. But I want to be clear. Drag is more than just this. I know all you see here is a bunch of letters. V, of course, represents how fast the object's traveling. So we're dealing with a force that is proportional to the speed of the object. And this force generally is acting to slow the object down. But ultimately, what you must understand is that K is just a letter we put here that actually describes a multitude of things about the object. It's not just, there's some specific constant called the drag constant. There really isn't. There's a whole group of things that collectively get put together to describe how drag functions. So for example, a simple example of that is just to watch something like this. I have a coffee filter, and if I drop the coffee filter, it takes a long time to reach the ground. By long, I mean under the standards that we've talked about, but hopefully the thing you recognize is that it doesn't seem to accelerate. It generally seems to move at a constant speed. Do you guys kind of agree with that? Now, I have something that is the exact same shape, but it does clearly accelerate. Now, you know the difference. One was more massive than the other, but isn't it true that so far, most of the time this year, mass has tended to cancel out, especially when we talk about dropping an object? Well, the other thing I can do is I can probably make them fall at about the same rate. Right? Now, I didn't change the mass of this one, but I did change how the mass was spread out. See, one of the things that contributes to how much drag an object experiences is what's known as the surface area to mass ratio. It's a ratio between how much space something takes up compared to its mass. It's in the variable k. It's wrapped up in there somewhere. So the variable k actually has a lot of things involved with it, not just some variable that we say this is the drag coefficient. And things like the shape of the object, the mass of the object, the cross-sectional area of the object, all of these things contribute to what that value of k is. Now, objects that are falling through the air or traveling through the air can manipulate k as they move in order to change the value on the fly. That's what a person who is skydiving is doing. A skydiver changes their shape. They tuck, they spread their arms out, they build flaps into their diving gear and their diving equipment so that they can change their cross-sectional area relative to the direction that they're moving. And I am confident that dozens of you have seen movies in which people are skydiving. Generally, the camera is falling with the skydivers. So you get this sense that they're just kind of all floating around in there. But they're not, they're falling. And they're manipulating how fast they're moving through the air by changing their value for k. In fact, the moment they pull their chute, suddenly their cross-sectional area expands greatly. And when it does, they seem to be yeeted right out of the groove. It's not exactly what's happening. The thing you have to consider is that when we're dealing with any kind of drag force, since it's proportional to the velocity, when you first release it, when the object's velocity is 0 and you just let it go, that moment, the only force acting on its gravity, and it will accelerate downwards. But within an instant, although the weight doesn't change, because it begins to move, a small drag force begins to be developed. This reduces the downwards acceleration. still falling downwards, but it reduces the downwards acceleration. So if we wait a little bit longer, the drag force, of course, will continue to increase, even though the weight is not increasing. And then finally, we will reach a point where the drag force and the weight are equal. This will be true regardless of the type of drag, whether it's directly proportional or proportional to the square or proportional to some other function. The thing to understand here is that this point represents something specific, a net force of 0 that is reached due to the motion of the object. It currently still has a drag force that is proportional to how fast it's going, but it's no longer going to change its speed because it's reached a net force of 0. That makes this the terminal velocity. Setting those equal to each other, we find that the terminal velocity equals mg over k. Now again, k is a measure of a lot of things, and you can manipulate k. So if a skydiver is falling through the air, the rate at which they're falling will depend on their shape relative to the direction they're moving. That establishes one terminal velocity. But if they suddenly increase k by, say, deploying their parachute or changing their shape, then they can suddenly increase their drag velocity. Their drag force. This is how they slow down, right? A sudden change in k, deploying their parachute, suddenly changes the equation. They're going fast, faster than their terminal velocity was before. That sudden change in the value for k instantaneously creates an unbalanced force upwards, which slows them down. They do this while all their friends are skydiving and they don't pull their chutes. They keep falling at the terminal velocity while this person slows down dramatically. That's why they appear to suddenly just leave the group and go upwards. They didn't go upwards. They're just not falling as fast as everybody else is falling. And that's kind of how that works. That's what you're seeing when you're watching skydivers. Now, and in all fairness, you're going to see this probably not for the first time, because we've talked a little bit about it, but you're going to see the entire process for the first time. And it does have a tendency to be a bit overwhelming. When it's all done, I'm going to split it up into groups and kind of give you what is expected of you in the coming weeks. But I'm also not going to shy away from the math that you have to be able to do. So there's going to be a lot of it for the next few minutes, and if the math is going to make you scared, just be patient. Most of what you have to do is very simple. So, but there is part of this that's going to be kind of tough. So what I want you to do is I want to talk about how long does it take to go from here, an object that just dropped, to terminal velocity. What I want you to construct is velocity as a function of time for this system. Now, to begin, what you will be asked on the exam, if this problem comes up, and this is the most common version of this problem. So when I say most common, this exact problem has appeared on the AP exam at least 10 times over the course of 30 years, so 50 years. So 10 times, that's 20% of the time, this is the version they choose. There are some variations. One variation is to have an object already have a velocity and have it encounter a region of space where there is some drag force that is, going to slow it down, but it has an initial velocity, but no weight pulling it down. Does that make sense? It's similar. A couple years ago, they didn't use coffee filters. They had a graduated cylinder filled with a viscous fluid, and they dropped BBs into it.
It really threw kids, but all it was is when the BBs were in here, they were experiencing a drag force that was upwards of kV, and there was weight downwards mg. It was somehow, because it was in a fluid, that students didn't see that this is the exact same kind of problem. So don't be thrown off. There's likely to be a problem where you will have a force that is somehow proportional to velocity. Generally, the first thing that you will be asked to do is to write out a differential equation that could be used to solve for velocity as a function of time. This is where the bulk of the points is going to come from. They're likely to give you the answer. In fact, they'll probably say in the next step, using your differential equation, use integral calculus to show that the velocity is this function. They're likely to give you the answer. But ultimately, most of the points is in this question. So the question again is, write a differential equation that could be used to solve for the velocity as a function of time. This is a force problem. So we start with net force equals ma, because in the beginning, the forces are unbalanced. The next thing that we have to do is kind of deal with the forces. There's two of them. So setting downwards as the positive direction, which is what I would encourage you to do, we have mg minus kv equals ma. Now, this part, it doesn't matter whether we use this form of drag or this form of drag. The process is the same. So the other version would be mg minus kv squared equals ma. Doesn't make a difference which one of these we choose. Now, the next step is the critical one. This is where you create a differential equation, and all you have to remember is that acceleration is your differential. So the moment you replace A with dv dt, you've created a differential equation. Sometimes this is worth up to 3 points. It is not uncommon for them to give you points for each of those steps. 1 point for understanding that you're going to start from Newton's second law, 1 point for knowing to plug in dv dt for A, and then 1 point for writing a differential equation. Since generally the rest of this is only given 1 or 2 more points, this whole thing is usually no more than 5 points, with 3 of the points coming here. So to me, there is absolutely no one in the room who can't do this part once you recognize this is what they're going after. Now, if the next statement is, now using your differential equation, find a function of the velocity as a function of time, now you got some work to do. Now you got to do some integral calculus. But most of the work is just algebra. Most. It's not easy. We're going to use this as our function today. And then in the coming weeks, we'll use this one as our function. We'll just do one at a time and we'll practice. So we're going to start here. And the next couple of steps, if they break this up into multiple points, the next couple of steps is just algebra, and you'll probably get a point for this set. What you have to do is something called splitting the differential. So this is the next part, which is going to be what you have to do to set up the integral. Not complete the integral, just set up the integral. And we've talked about this before. I'm just going to talk about it again. So focusing on just the function that's bracketed, your first job is to split the derivative, which means multiply both sides with whatever is on the bottom of the derivative. And for us, it'll always be dt. So mg minus kv times dt equals m dv. That's just splitting the derivative. After this, the next step in splitting the derivative is to collect like terms. So this is splitting the derivative. And now we want to collect like terms. Collecting like terms means specifically to put v on the same side with dv and t on the same side as dt. Now, since there is no t in this function, we just have to make sure this whole thing gets to the same side as dv. So I'm just going to use division for that. Write it as a function times the dv. Separate them out a little bit because calculus has some symbology, and we're trying to stick with the symbols that they use. So having your differential apart from your function is kind of critical for that. Now, the next step is to establish your integral. And set your boundaries. All this is drawing the fancy S's. And remember, they just represent sums. However, you need to set your boundaries. And this part is different depending on the problem. So the real thing is you'll be given to what to put at the bottom here. But you need to know what to put at the top. The bottom is going to be the initial conditions. So for example, our time starts at time equals 0. And our object was dropped. So at time equals 0, the velocity was 0. So you're establishing your boundary conditions. You guys who are in calculus and have done integral calculus already know that in Calc AB and BC, you generally do every integral as an indefinite integral, and you put your boundary conditions afterwards because you will always have a constant. There's no difference. You could do it that way if you'd like. The AP Physics graders understand how math works, so if you do it that way, that's fine. The difference is that every single grading guidance I've been given expects to see the limits placed on the integral themselves. So that's why I teach it this way, but it's mathematically identical to do it as an indefinite integral and leave the constant and then plug in your boundary conditions at the end to figure out the value of the constants. So those of you who had calculus know the language I just spoke. Those of you who haven't had calculus, I know. You don't know what I was talking about. But we have both people in the room. The upper boundaries are function variables, meaning we're trying to create a function. So the upper variables will be the functional variables. For example, we want v as a function of t. So we just put v as a function of t at the top. Now I know that there's a lot of v's there. If that bugs you, then put v with a little t next to it like that to remind you that this is supposed to be a function. At the end, we'll be solving for that. If they're going to give more than 1 point for doing the integral calculus, that is it. They will look for you to set up the integral. Again, we have done no calculus yet. You understand that, right? All we've done is some algebra manipulation. Okay, so what we're going to do next will be worth the last point. But I have news for you. This is going to be long. I will make sure every single step in algebra is done. And I would encourage you, and I'll be slow and I'll be diplomatic, but write some notes about what we're doing in every step. I think it will help you, because if you can replicate this, you can do it. Now, at the same time, I'm going to give you some advice when it comes to points at the end of this, and you may never do this on your exam. And there's good reason to not do this. You'll see in a minute. But we're going to do the calculus now. Now, if you remember, taking an integral requires you to find the antiderivative and then plug in your limits of integration. And that's what we're going to do here. You need a way of finding the antiderivative of both sides. You've learned a couple of rules, and we're going to use those rules. One of the rules you've learned is the polynomial rule. So the left side of this, we're going to use the polynomial rule because I'll notice that this is the integral of dt, but there's nothing there. If there's nothing there, we assume a 1 is there. We don't write it as a 1, we write it as t to the 0 power. You should remember this from way back in September. Now, once we establish the t to the 0 power, we find the antiderivative first. That's this step. Now, the antiderivative of a polynomial is to add 1 to the polynomial and then divide by the new, add 1 to the exponent and then divide by the new exponent. So this will be t to the 0 plus 1 divided by 0 plus 1. We add 1 to the exponent and divide by the new exponent. That's the antiderivative. We also need to set the limits, the boundary conditions. So once we have found the antiderivative, the integral symbol disappears, but we write in our limits, 0 to t. And that's going to equal whatever the same thing is on the other side, the antiderivative and all that on the other side. But we're going to do one more step on the left side since this one we can do. It's pretty easy. T to the 0 plus 1 is just t to the 1 divided by 1. So all of that is just t. Our last step in doing an integral is after we find our antiderivative and we simplify it, you plug in the top limit and then you subtract and plug in the bottom limit. So this will be, we'll plug in t for t and then subtract and plug in 0 for t. All right, so now the other side. There's problems with the other side, a lot of them. First, that looks way more complicated than just t to the 0 power. Right, it's got a v in it, and that's what we're looking for because we're supposed to be setting v as our important variable, but v is under here. Now, even if the whole thing was just 1 over v dv, we would have trouble. Do you know why? There's a problem. We can't use the polynomial rule here, can we? If you don't see why, let's evaluate this for a minute. This would be v to the negative 1 dv. If we use the polynomial rule, it would be add 1 to the exponent and then divide by the new exponent. And you see that you can't do that, right? So that's a problem. We can't use the polynomial rule on the inverse. It's the only polynomial that won't work with the inverse function. Now, your AP equation sheet actually has all of the possible integrals you will be expected to do. And there's only 3 that aren't the polynomial rule. This is one of them. The antiderivative is the natural log of v. I'm going to write all 3 that you will need to know, so you have them in a table. Aside from the polynomial rule, there's the inverse, there's the trig function sine, which is minus cosine, and there's the integral of the trig function cosine, which is sine. I take that back, there's one more. You'll need to know the integral of e to the x, which is just itself. Those are the 4 that are on your integral table. The integral table has more things, like it has what happens if there's coefficients in front of these letters. But these are the ones you'll eventually have to know. We are going to focus for the time being on this one. But even so, that's not what we have here. We have to try and make what we have here look like that. And the reason why we want to make it look like that is because V's in the denominator. So we're going to try and make it look like something in the denominator. So, fun times. There are a couple things that you guys should learn to do, and let's go ahead and hit the easy ones. For example, any constants that aren't attached to a variable, they can be pulled out. So I can pull this constant out, because it can be factored out of the equation. So I'm going to write this as m times the integral 0 to v of 1 over mg minus kv dv. There's nothing in the denominator that I can factor out, so I'm stuck with this. U sub is an attempt to put in a substituted expression that will simplify your integrand. So for us, that substituted expression, I think, is everything that's in the denominator. If we say that u, and I don't know why u was chosen, when you guys get involved with this, you might find that to get an integral to actually get to a point where you can do the work, you might have to do 2 or 3 substitutions in a row. That's happened in my other class, E&M, where we've had more than one substitution that had to be made. That's not generally the rule, and it would never be on the exam. But a single substitution is within your capacity and might be on the exam. This substitution is we're going to do mg minus kv. But to do u sub, you can't just sub in the function. You also have to sub in for the derivative. So we need to replace dv with du. So we take the derivative of our substitute function. Now, mg is a constant, so the derivative of a constant is just 0. But minus kv is a polynomial. I will use the polynomial rule to take the derivative with respect to v and find that it's just going to be minus k times v to the 0 power. So just minus k. Now we need to solve this for dv. So I'll just cross multiply and find that dv equals du over negative k. And now we have something to sub in for dv and something to sub in for the denominator of our function. So that's what we do next. So over here, m times the integral 0 to v of 1 over u times du over negative k. Negative k is just a constant, so it could be factored out of our integral completely, and I'll do that next. This matches what we just talked about. It's a known integral. All we have to do is do the antiderivative and plug in our limits. So because we know this one to be the natural log, all we have to do is write in natural log of u. But our function wasn't about u. Our function was about v. So before we can plug our limits back in, we're going to plug our function back in. Now, all right, so that takes us to here. Oops. Said that and just didn't do it. All right. So in one more step, the calculus will be done. That's plugging in our limits. So you understand why the absolute value bars have to be there. They're there because you can't take the natural log of a negative number, and because I have mg minus kv to ensure mathematically that we stay on the positive side of that. But as we described, there should be no reason for that to occur. So we've done all the calculus. This is where the calculus ends, but we're not done. You're supposed to come up with an expression for v. So from this point forward, it's algebra. And you guys are good algebra students. You can do it, right? So you know how to go from here to v equals, or would you like me to step through that as well? Yeah. Okay. Just checking, because I assume this was on your test today. So I want to isolate v, and you kind of see that it's buried, right? So there's a couple of algebra steps here. Let's start by, let's move that m over k to the other side. That'd be a good place to start. So minus k over m times t. And when I said I was going to do this one step at a time, I really meant it. I'm going to go nice and slow. Now, I want to isolate v, and look, it's inside a natural log. I know that if I raise the natural log to its base, then I can cancel out the natural log. So to do that, one way to make it easier on myself is to combine this into a single natural log. And when you subtract logarithms, they're exponents, so you divide them. So this is going to be the natural log of mg minus kv divided by mg. It's not the only way to do this. This is just the way I like to do it. And you've already been taught this, I believe. Now, once you get here, I can raise both sides to the same base. So the base I want to use is the exponential. So e to the minus k over mt equals mg minus kv over mg. Now, I'm still trying to isolate v. So the next step, I think, would be to multiply both sides by mg. Yep.
Why couldn't you just cancel out the mg's right there?
Well, because it's mg minus kv over mg, so I could, and I'd have 1 minus kv over mg. And that's okay. I mean, that's another way. That's not a route, but I can't just get rid of the mg because it's going to be under both terms. I'm going to end up factoring it out in a minute anyways, but let's go ahead and manipulate this to get kv on the same, by itself and not negative. And now I'm thinking, I'm going to factor out the mg, and you'll see why. But I'm going to factor it out. That'll give me mg times 1 minus e to the negative k over m times t. And this is kv. One algebra step at a time. And now I will divide both sides by k. That's the answer. Here is where we set up the integral. This 1 point on the exam. So now I would argue we did this with a lot of steps in there that perhaps you could condense. On the other hand, and hear me out, the most likely thing they will say on the exam is show through integral calculus that your differential equation is, and they will give you the answer. If you make it to here, and then after this, just write in the answer, they're likely to give you full credit. They're not testing calculus. Does everybody understand? Now, if you can't make it to here, just use their answer and move on and lose the 1 out of 15 points and still get a 5. Don't do this on the test. You understand there's no reason at all to do this on the test. Do you have time? No, you don't. There's no point. So please, if you're sitting there twiddling your thumbs because in those 45 minutes you did every other problem and you have 10 minutes left, okay. But I don't think you will have that kind of time. Right? I just don't think it's going to be there. Let's talk about this answer though. First, what is this? The very beginning of our conversation. What is it? That is the terminal velocity. That's right. It showed up. It had to. Now, help me out with this because you guys know things, I think. What is this term when t is 0? 1. What is 1 minus 1? So do you see that when we put in 0 for t, we get 0? We forced that on the problem. It had to be a result. We set those limits of our integral, so it had to obey if we did the math right. It's how you test to make sure your calculus is right. You plug in your limits, your boundary conditions, and see if you get what you expect. However, what happens when you plug in infinity for t? Now, you guys did all that limit crap at the beginning of your calculus year, right? You understand that first, infinity isn't some fabricated idea. Infinity is just a very long time or a very big number. Big compared to the other things that are there. Infinity for this problem could be a couple of seconds. Just long enough to reach terminal velocity. It's when you have reached a point where increases in t don't really change your problem, you're at infinity. So don't think infinity is unattainable. Things reach terminal velocity all the time. So infinity makes this term 0. And that means you're at terminal velocity. Please grab your calculators. I need you to do something. And we are short on time, so you'll have to hurry. Way short on time. So we won't have time for this. I want you to do this, though. Using your graphing calculator, I would like you to plot the following things. If you can, plot them all on the same graph to see how changing any of these values changes the answer. You'll notice I've just manipulated what's up here.